everyone, welcome back to the channel. So today in this video lecture we're going to be solving this problem, that is design, add and search words data structure. So this is yet another problem in the series and it is also solved using the tries. Now how this problem is different, how design, add and search word data structure is different from tries, because we have already designed a data structure which supports these two functionalities. Let's read the problem statement. Again, we have to design a data structure which supports these two functionalities, that is adding a word and then searching a corresponding word. Now we must have two functions. First one is add word, which adds the word into the trie, into the data structure. Then we must have a search functionality which search for a word into the word dictionary data structure, and we have a constructor which initializes an object of this class. Okay, now here in this add words function we simply adds the word to the data structure so that it can be matched later. There is nothing new in this as we did in the trie. But in this search function we have something different, because the word may contain dots and the dot can be matched with any character. Okay, so let's just understand what does that mean. So let's say we had inserted bad into the trie. I had inserted bad, I had also inserted CAD, and now I want to search for .AD. Okay, can I now I will ask whether this .AD is present in the trie or not. That means I have to replace this dot, the very first character, with a character such that the resultant word is present in the trie. One of the optimal ways to do so is simply replace this dot with B, so it becomes BAD, and this is indeed present in the trie. We have bad here. We can also replace this dot with C, it becomes CAD. It is also present in the trie. So that's how we have to make this replacement, that is replace the dot with some character such that the resultant word is present in the trie. That's what the problem statement says, and that's the thing which makes this problem a new problem. Okay, so let's see how we can solve it. So let's better understand it using an example. So in this very first example, the very first instruction is word dictionary, that is initialize an object of this word dictionary class. Then we have add word call, that is add a word which is bad into the trie, into the word dictionary. So let's do it. So let's add the very first word which is bad. I think it's bad. Okay, we had to add bad. So start from the root node, add B, then add A, then add D. We've already described how we do this, so and mark this D as the ending character. Then we add dad. Okay, so add, the very first was add bad, then we had add dad, then so let's add this dad. So we have D as a child node for root? No. So we add this D, then we add A, then we add D, and this is the ending character. Then we add the next word which we have to add is mad. We add mad as well. So do we have M as a child for root? No. So we add M as a child, then we add A as a child, then finally we add D as a child, and we mark this D as the ending character or the ending node. Then we have search functionality. Now I want to search for this bad. No, I want to search for this pad. Do we have pad in this trie? So what I'm asking is search for the pad. Do we have P as one of the child for root? No, we don't have it. That means this is not present. So we return false for it. Let's see the next one. that is search for bad. Do we have bad in the try? So we have search bad, B-A-D. So do we have B? We start from B, character B. Do we have B as one of the child for root node? Yes, we have B here. Then do we have A as one of the child for B? Yes, we have A here. Do we have D as one of the child for A? Yes, we have D here. And is D marked the ending character? Yes, it is marked. That means this path constitute this word which we are looking for, that is bad. So we return true in this case. Okay, let's just move to the next instruction, which is again we want to search for .ad. Okay, so search .ad. Start from the very first character, it is dot. And again, dot is not a child for root. We never inserted a word which contained dot. That means we have to replace this dot with some character which is present as the child node for this root node. And we have three such child nodes. So either replace it with B or D or M. Which one will give a valid answer? It depends upon the fact whether the remaining substring AD is present in the subtree of the character which I have chosen. Let's say I choose B. If I have chosen B as a replacement for this dot, that means in the subtree of B, like in this subtree, we must have AD as one of the paths, and D must be marked as the ending node. Fine, that is D, character number D corresponds to the last node in that path. That's what we have to check. Okay, and that's all. To do so, we create a search function, and we have to modify the search functionality which we defined in the previous video a little bit. So how do we do that? Let's see. Like in this case, if I replace this dot with B, then we do have a valid path in the subtree of B which contains A and D. Okay, and AD is a valid path where the path ends at D, and here D is the last character. So we return true because we convert this character, we can convert this character into bad, and this is present. We can also convert it into dad. We can replace this dot with D, this one, because AD is also present as a path in the subtree of D. So we can replace it with D as well. We can also replace it with M as well, because AD is present here as well as one of the paths in the subtree of character M. Fine, so let's just see how we can implement this functionality, or let's understand it with one more example. Okay, to implement this type of search functionality, what I'm going to do is I will be using a search function. So let's say a search function which has two values, the node on which I am standing and the character on which I am standing. Fine, so initially the node is root node, so we call this search functionality for the root node. So search is called for the root node, and the character on which I am standing initially is also 0, or it is the character at the 0th position. So let's say I'm searching for .ad. I'm starting the search functionality from this character and from this node correspondingly. Fine, and let's just see. So let's just check. So we encounter a dot here at the root. What I am going to check is we have three childs here for the root node for the node number 0, and I'm going to replace this dot with one of the childs, and I really do not know which choice is going to give me the answer. That means I have to choose every single child for the root until I don't get a valid path. Fine, so let's first choose this B, trying to put B at this position, and that means recursively call this function search because I found a dot for character number 1 and node number 1. Why? Because you see, I'm replacing this dot with this B, And what I'm saying, starting from the character number 1, which is A, till the last character constituting the string AD, whether this string is present in the subtree for the character B. The search function basically searches for the string which starts at character C and ends at the last character into the subtree of this node, and initially this node is the root node and it is node number 0, and I am looking for the string which starts from 0, that is the entire string. And since I encountered a dot, I am trying to put one of the child nodes for the root node at the position of this dot. So I put B here. Since I am putting B, I demand that the remaining string, which is AD, must be present in the subtree for the node number B, okay, here in this subtree. And that's why I'm calling the same function recursively for the child node, okay, because you can see that here I'm calling the same function for character number 1 and for node number 1, which is this node. Fine. Now start from node number 1 and iterate over its child nodes, correspondingly checking whether we have a character which is present at index number 1, which is A. So I'm looking for A into the child nodes of B, and we do have A here. I have found A, that means move to the next character. We no longer need to recursively call the function because I'm getting my characters. So call for D, so like look for D into the child nodes for node number 2, for child nodes of this node. Do we have D? Yes, we have D here. We have found D as well. Since this marks the ending character, that means we have to check whether we have is and variable for this node to be marked true or not. Since it was marked true, that means I return true from here. I found D, that means I return true to the calling function here. This calling function 1 1, it returns true. Like this function which was called, it returns true to its calling function as 0 0, and in the same way this returns true to its calling function. So in this fashion I conclude that the word dot .ad can be matched with one of the words present in the trie. That's the procedure. That's the search functionality which I'm trying to implement here. Okay, so I hope you got the idea how we're gonna solve this problem. Rest stays the same. We know how to insert a word into the trie. We know how to search for a word. If we do not have dot, we just have to make a really little modification in the search function. So let's just jump to the code implementation part. So here we have our function, and apart from this class, let's create a trie node class trie node. Let's take two variables. The first one is basically the array of children, so it will be trie node which stores the pointers to the child nodes, so children 26. And then we have is and variable. It's the boolean variable which is used to mark whether a particular character is the ending character or not. Let's create a constructor for trie node. So for this constructor, let's initialize this is and with false. Let's initialize this children node with null pointer or a 0, size of children. That's how we prepare our trie node class, and here in this public part, let's create a root node. So let's initialize a root node. Let's declare a root node, and this root node is initialized in word dictionary. New trie node. Fine. Let's implement this add word function. So declare a node P, store root in it, iterate over the word. There's nothing new here, and check if we have C into the trie or not. So if we have C as the child node for the current node, children for C minus A, if it is null, if it is not there, then we have to create a pointer for this node, for this character, which points to a yet another trie node, and we move to that trie node. Children C minus A. Finally, mark the is and variable to be true. Okay, that's how we implement the add word functionality. Let's see how we can implement this search functionality. So here in this search functionality, first of all, let's declare this pointer trie node. P, initialize it with the root, iterate over the. Okay, since this is the search function, we have to create one more function, which is the helper function, because we know that in the search function here we need to pass two variables. The first one is the node on which you are standing, and the second one is the character. We have to keep track of two variables. So let's create a helper function. Let's call it search helper, which takes in the word and also the node on which I am standing. Here in this helper function, let's just iterate over the word which we are looking for and check if the current character is not dot. If it is a dot, then that means we have to make a replacement, and we'll iterate over the child nodes for the current node, which is P or node children. These are the trie nodes, these are the child nodes, and check if we have a non-zero child node. Means we have pick every position where we have a pointer, or pick every child node and try to put this child node at the place of that dot. And since I'm putting it, I have to call this search helper function for the word which starts from I plus 1 till the end and goes till end. So we use a function word dot substring, and we also pass this child node there. So if we find, so if this search helper function returns true, means we have found the remaining word and we can make this replacement. If we can make this replacement, we return true. Okay, otherwise we return false. And we do it for every child. We try to put every child onto that place of dot. Fine. And here at the end, return whether the last node is. Before that, let's say if this is not the dot, if we find a character which is not equal to the dot, if it is the case, then check if we have a, check if this word, check if this character is present in the trie or not on the path on which I am moving. So node children C minus A, if it is there, if it is not there, then return false. If it is there, then move to the next node. Okay. Okay, we don't have I here, so that's why I we must use a loop which iterates over every character like this. So word I goes till word dot length, and see C as let's create C as the ith character, and rest is good, and check if we have is and marked to be true or not. Node is and fine. So and from this search function simply return this search helper, call this function search helper, password and the root node. The root node is initialized to the try node. Okay, good. Let's just see if it works. It got accepted. Let's submit it. Fine. So let's discuss the time and space complexity for the approach which I explained here. We can see that everything is same. We are the time complexity for the add word function is big of n, where n is the length of the word which we are inserting. Also for the search functionality, the time complexity stays the same, because at the end of the day I'm iterating over every character at most once. Okay. So what will be the complexity for the search functionality? We can see that let's say I'm searching for something like this. Now to search for this type of word into the trie, we may end up traversing all nodes of the trie. And how many nodes can be there? If we have k words and the average length for a single word is n, then these are the number of characters or the number of nodes which we have in the trie, and we may end up traversing all of them. Fine. Now that means the time complexity can be big of k into n. Fine. So the time complexity for the search functionality increased because we have dots here. We have to take care of it, because let's just see why it increased in this case. Let's say I want to search for this in this, let's say I want to search for this type of word into this trie. So I start from the root node. I try to put B at the very first position. I put B here. Then I move to A. I try to put A here. Then I move to D here and I try to put D here. But I see that D do not have any child. So I have to come back. Start again from D. Try to put D. Then try to put A. Then try to put D. Again, we do not have any child for D. Come back. Try to put M here. Try to put A. Try to put D here. Again come back. We didn't find our word into the trie, but we ended up exploring every single node of the trie. That's why the time complexity is big of k into n, while the space complexity for the tries is the space complexity would be now we can see that we have a single dot, so it will be called 4 times recursively. That means we are consuming call stack. Fine, we'll have 5 function calls for this search, and we may have n dots in a word. So in a typical word we may have n dots, and this may be the largest word in the list or the dictionary which we are given. So the space complexity will be big of n, where n represents the largest word or the longest word in the dictionary. And this is not the auxiliary space but the stack space which we are consuming. The auxiliary space is constant. The auxiliary space is not this. This is the extra stack space which we are consuming. Rest of the space complexity is same as it is for the tries. Fine. So that's all. I hope you got the idea what we are trying to do, and in the next video I will be solving a problem over the tries. So